Welcome to the screencast of TiCoNE, the time course Network Enricher. What's TiCoNE? TiCoNE is a clustering method with focus on time series data, interactivity, and network integration. Clustering in general is a popular technique to identify groups of similar objects in large datasets. In our particular case, we are dealing with time series data, so each object is associated with at least one time series. We can then define prototypes for each cluster by taking, for example, the mean or the median time series behavior of that cluster. And this is already enough to define the core idea of TiCoNE. We start out with an initial clustering. We can then calculate prototypes for each of the clusters. And then we can assign all the objects to the cluster with the most similar prototype. Then we end up with a new clustering, and we can recalculate the prototypes and reassign the objects. Every time we execute these two steps, we call it an iteration. TiCoNE is an interactive method, so at each iteration you can interact with the clustering, for example by splitting up a cluster, by merging clusters, or by removing objects which do not really fit to their prototype. And there's more. For example, you can add predefined clusters, you can delete clusters, or you can tell TiCoNE to keep a cluster even though it will change during the optimization procedure. TiCoNE is available as a Cytoscape app, a standalone implementation, and a web application. To the end of this presentation, we have prepared a small toy dataset which consists of 3 clusters, each following a predefined prototype, which you can see here. Additionally, we generated objects for each of the cluster that follow the prototype more or less. To make the task more challenging, we also generated background, aka noise objects, which do not follow any pattern. Additionally, we generated a toy network which resembles the same cluster structure. Objects that belong to the same cluster are more tightly connected than objects of different clusters. The goal of this demonstration is then to recover the clusters we have hidden in data using TiCoNE. So, we are now in Cytoscape, and now I'm going to present how we can reproduce the results shown in the basic tutorial on the TiCoNE website with our TiCoNE Cytoscape app. So the first step is to import the data in the network. So to this end, I just downloaded the toy data from the tutorial website, and I'm going to import them now. So let's start with the network. Here we're going to tell Cytoscape that we don't have a header line in our file and which of the columns in the network file corresponds to source and target of our edges. Now Cytoscape is performing a basic layouting to make the network more appealing. So you should end up with something like this. Next, we import the time series data as a table, also using the Cytoscape import functionality. We give it a name that we can recognize, and again we remove the option that we have a header line in our file. Alrighty, so now we can start using the Cytoscape app, our Cytoscape app, and to this end we look on the left hand side to the TiCoNE tab. So here we have a sub-tab called New Clustering with a lot of different settings, and here I'm only going to explain the most important ones. So of course we need to select the table that we just imported. Then we get a small preview of the first line of this file or table, and this can be used as a quality control that you have selected the right columns for the object ID, the replicate, and the time point information. So you can also customize this if you choose the change column mapping. Furthermore, you can pre-process the data, so you can remove objects that you don't like or that you feel are not fulfilling the quality control or which are not present in the network that you have imported. Furthermore, you can also change the discretization of the time series data. So we will just leave this at the default. So we have 10 possible discretization, discretized values in the negative range and 10 in the positive range. Regarding the clustering, we choose Clara as our supplementary clustering method. So this means this will be used for the initial clustering. And if we split up a cluster into multiple subclusters using a clustering, then also this clustering method will be used. Furthermore, we want to start out with 10 initial clusters and using Clara. We will use the mean aggregate function to calculate our cluster prototypes. We use the Euclidean distance as a similarity function for objects and clusters. And we could import additional identifiers for our objects in the time series data, which we are going to ignore for now. So, and then we are ready to start the clustering. So we click on Start, and then we are presented with a little warning because we currently have a network view open. So this can degrade the performance of the clustering process. So we will just confirm this with yes, and then the network view is removed and the clustering is performed. So now we see on the right hand side in the results panel our initial clustering. The most important part is this table where each row corresponds to one cluster. And for each cluster we have a lot of information. So we have a cluster ID, we have the number of objects in the cluster, we have average Pearson correlation of objects to their cluster prototype, we have the average residual sum of square of the objects to the cluster prototypes, and if calculated, we have a p-value. Additionally, we have a visualization of a cluster which contains the cluster prototype as a bold black line, and colored lines correspond to the object time series. We can open a larger version of this chart when we click on zoom. Then a dialog will pop up showing us the cluster in bigger size, and we can also resize this window. The clustering table allows us to sort our clusters by these attributes as well. So for example, we can cluster them by the cluster ID or their size, or by the similarities of the objects to the cluster prototypes. Furthermore, we see specific operations here. For example, we can use the delete function of clusters, or we can split up a cluster here on the right hand side. So operations specific to one particular cluster can be found under the cluster visualization on the right hand side. More operations can be found on the left hand side panel. For example, merge clusters or filter objects. We can also perform iterations. We can either perform one iteration at a time by clicking on the next iteration button, or we can perform iterations until convergence, meaning until the clustering doesn't change anymore. So now I'm going to present some of the human augmented operations. Let's start with removing non-fitting objects from a cluster. So here we just choose any cluster, for example cluster 7, and we click on delete under the cluster graph. Then we are presented with multiple options. So here we are choosing least fitting objects. And then we are presented with a chart containing the least fitting objects of this cluster. Here we can choose which similarity function we want to use and how many % we want to remove. So now we are just choosing Euclidean distance and we're keeping 10% of the cluster, and then we click on delete objects. So now cluster 7 contains 10% less objects. Another operation is to split up a cluster. Let's for example split up cluster 6. So we scroll to cluster 6 and click on the split button under the cluster chart. And then we are again presented with multiple options how we want to split up the cluster. So here we want to split it up based on the two least similar objects using the Euclidean distance. We are then presented with such a panel where we see the current cluster on the top and the two new clusters below. And we can then decide whether we want to keep these new clusters or not. So here we are just saving them, and then again we are presented with these new clusters in the cluster table, and we can choose do we want to apply these or not. Another powerful operation is to suggest new clusters. So this can happen in multiple ways, either based on least fitting objects or least conserved objects, where least conserved objects correspond to these where multiple samples do not correspond well to each other. So in biological terms, non-reproducible experiments. Or least fitting objects means objects that do not correspond well to their cluster prototype. So we will choose this one. And again, we are presented with a dialog with 10% of the least fitting objects of the overall clustering, and we can choose again which similarity function we want to use. So here we are choosing Euclidean distance. We can click update. And then we can choose how many new clusters we want based on these least fitting objects. So here we are just keeping the default 3, and we click on suggest clusters. We then get a preview of the 3 new clusters of the least fitting objects. Then we can save or discard these new clusters. If you're in doubt about an operation that you performed, you can use the history functionality. The history functionality allows you to go back to any previous iteration that you performed. You can then also decide to go back to that particular iteration and use it as a starting point to perform new iterations. As you can see, currently we do not have cluster p-values in our cluster table. This is because cluster p-values are computationally intense and they are not implicitly calculated. To calculate them, we go to the left-hand side to the calculate cluster p-values functionality. And here we have multiple options that we can set. First, we can decide which function should be used to generate a background distribution for our p-values. Here we just leave it at the default, permuting prototypes over time. So this just takes our current prototypes and shuffles them across all time points. Next, we have to decide which features of the clusters should be incorporated into a cluster fitness score, which is then compared between our current clusters against the background clusters. Choosing the default features, number of objects, and average similarity gives an indication of how well the fit of the cluster is in terms of objects to their cluster prototype. Lastly, we need to choose the number of permutations we want to perform. The larger this number, the more accurate our p-values will reflect the true probabilities, but also the longer the computation will take. After we have set all these settings, we click on Calculate p-values, and the cluster table on the right-hand side will be updated. In order to continue using these clusters in more advanced calculations such as comparison or connectivities, we can now filter these clusters such that we only use the significant clusters for the follow-up operations. To this end, we browse to the left-hand side and scroll down to filter clusters, and we choose p-value, and we set a p-value cutoff of 0.01. Then we click on Apply Filter, and the cluster table will be updated, and all filtered clusters will be shaded gray. If we now click on the column header of the selected column in the cluster table, we can select all the clusters that were not filtered out. Another core functionality of TiCoNE is the integration with networks. So now let's visualize these clusters on our network that we have imported. To this end, we have to recreate a network view for our imported network. And we then browse to the Network Operations tab of TiCoNE and click on Colorize Network. This will color the nodes of the network according to the selected clusters. Nodes that do not correspond to any of the selected clusters will be colored black. Next, we can perform a network enrichment using tPath Miner. So here we have to select the network that we imported, and we have to specify the KPM parameters, such as the number of exception nodes and the number of subnetworks that we want to identify. We just leave these settings at their defaults, and we click on Perform. This will now search for subnetworks in our imported network that are enriched in objects of the selected clusters. Since we selected 10 subnetworks, we now get a list of 10 such subnetworks that are enriched in our objects, and then we can select any of those subnetworks and get a highlight on our imported network where these nodes are located. If we select multiple such solutions, we can either show the union or the core of the selection of subnetworks. So here we select the 5 first solutions corresponding to subnetworks, and we click on Show Union of the selection. And then we get a new network which only contains nodes of these 5 subnetworks. To get a better overview which nodes correspond to which cluster, we can colorize our clusters.